Good morning. I'm Doug Ming from NASA's Johnson Space Center, and it's my honor to introduce our next two speakers. First of all, I want you all to put on your seatbelts, get ready to blast off from planet Earth. We are now heading out into the solar system, and our destination is Mars. I was thinking about the 100th anniversary of MSA, and 100 years ago, Mars was a really heated debate among scientists. It wasn't about the minerals. It was about if there were canals on Mars that had been developed by some extraterrestrial beings. Percival Lowe first presented that hypothesis, but as telescopes got a little bit better resolution, his hypothesis was met with a lot of skepticism. In fact, that debate raged for quite a few years, and then finally in the 1960s, NASA sent a flotilla of spacecraft since that time to Mars, and we now know that Percival Lowe's hypothesis was not correct. We did not see these extraterrestrial channels. But this flotilla of spacecraft that got to Mars has given us an incredible amount of information about Mars, and we'll talk about that this morning. Before I go on, this flotilla that I was talking about, we have Dr. Jim Green. Jim in the front row. Jim is NASA's chief scientist and was the director for the Planetary Science Division at NASA headquarters. He led the science missions here at NASA, these robotic missions to Mars and beyond, as well as the research. So it's great to see Jim here. First of all, I'm going to introduce the two speakers. The first talk, and what you're going to see here is a very dynamic difference between the two, the information you'll hear this morning between the two speakers. The first talk is about the surface mineralogy and geochemistry and what we have determined by these landers and rovers that have got to the surface. And particularly this morning, we're going to hear about the mineralogy from an X-ray diffraction unit, and it's so fitting that the first X-ray diffraction unit on Mars happened 100 years after Lau first used X-ray diffraction. So it's pretty cool that we're able to expand that from planet Earth and take that to Mars. So we'll hear Liz Rampey talk about the mineralogy that has been determined by this Kinman instrument in Gale Crater. Then we're going to look at a very different part of Mars. And Dr. Hat McSween from the University of Tennessee will talk about these meteorites that we have in hand here on Earth and how they are different from the things that we see on the surface. So with that, I'm going to turn it over to our first speaker, Liz Rampey, to give her talk, which will be on looking at Mars's ancient mineralogy and doing that through the eyes of X-ray diffraction.
Thanks for letting me participate in this birthday party. Like many of you in this room, MSA was the first scientific organization that I joined. 100 years ago, MSA members didn't worry about the mineralogy of other worlds. That changed 50 years ago next month when the Apollo astronauts started bringing back samples of the moon. 40 years ago, Ed Stolper and I, both of us were graduate students who didn't have a clue that we might be stepping on a hornet's nest, proposed that a couple of unusual meteorites that nobody seemed to be paying attention to might be Martian samples. And we got laughed out of the room. The evidence, though, that convinced a lot of people that we really might already have samples from Mars came from some nice studies just a year or two later done by scientists who were analyzing rare gases that were trapped in impact melted glass in these meteorites. And the trapped gases implanted during the shock matched very precisely the composition of the Martian atmosphere, as you can see over here. And this evidence still stands as the most convincing of the lines of argument that these are really Martian samples. So what are they? Well, with only one exception, they are igneous rocks, and they come in a number of flavors. The first are the shergottites, which are by far the most common type. Also, all shown in thin section here. Over here are the basaltic shergottites. They are rocks composed of pigeonite, augite, mescalinite, which is plagioclase that has been turned into isotopic material by shock, and titanomagnetite. There is also an olivine ferric variety. It's basically basaltic shergottites with olivine phenocryst, and the olivines here have this peculiar brown color, which appears to be due to the fact that some of the iron in the olivine has been oxidized by shock. And then there are the poikilotic shergottites. They used to be called layersolitic shergottites because the first ones of these that we had to study were relatively small samples, and all we could see in a thin section was large orthopyroxenes enclosing olivine and some chromite. But subsequent finds of these showed that there were also areas that contained plagioclase, or actually mescalinite, as well as clinopyroxene, and so their compositions are really more like gabbros than ultramafic rocks. So the shergottites are the first. Then we have the knocklites, as shown over here. The knocklites are cumulates of augite with a little bit of olivine. The chassignites, there are only two of them, are olivine cumulates. And then the most recent find are augite basalts. There are only two of those that we've found so far too. And those are augite plus plagioclase, and they're, at least some people think that these basalts might be like the parent material or the complementary material to these cumulate rocks. And then finally, we have two oddballs. One of them is Allen Hill's 84001. It's a cumulate of orthopyroxene. It is arguably the most famous meteorite in the world. And the reason it's famous, or I would prefer to say infamous, is it is the meteorite for which a number of years ago arguments were made that it contained evidence for Martian life. I'll come back to that at the end. And then finally, there is the Northwest Africa 7034 and its pairs, a number of other meteorites that were probably pieces of the same fall but broke up in the atmosphere as they came in to Earth. And this is a regolith breccia. It's arguably the kind of orangish squares, and it's, the bulk composition is compared with the Earth. You can see that there are a few differences. I should say this is the bulk silicate planet in both cases. The mantle plus crust, it doesn't include the core compositions, although the meteorites, their depletion in siderophile elements also helps us to constrain that. Another interesting thing that we know from Martian meteorites that we haven't learned from exploring the planet otherwise is that it has a distinctive oxygen isotopic signature. This is the ratio of oxygen 17 to 16 versus 18 to 16 relative to a standard. And here's the terrestrial mass fractionation line along which all terrestrial samples plot. And here are the Martian meteorites. They have their own mass fractionation line that is deflected from the terrestrial line, indicating a different reservoir of oxygen. Martian meteorites formed by melting of ancient mantle sources that had distinctive properties. They had distinct radioisotopes. One example is shown here, tungsten 182, and you can see a big range in compositions of these that reflects different mantle sources. Another difference is in their trace elements. Here is the ratio of lanthanum to ytterbium, which is basically an indicator of the degree of compatibility or incompatibility of rare earth elements, and it's plotted against the oxygen fugacity relative to a buffer. And there are actually a couple of trends here. The basaltic shergottites show one nice trend here, but we have both enriched in incompatible elements and oxidized and depleted and reduced. And then the poikilotic and olivine ferric shergottites show a parallel trend, but again, enriched, oxidized, depleted, and reduced. So we think that reflects different mantle sources, although some people prefer a mantle source and contamination with a crustal source. Another way to show trace elements, and it's really very difficult to do trace elements by remote sensing so far. We can get a few, but we really need the meteorites to do these. And these are all the data that I can find, plotted on what's called a spider diagram, which basically is in terms of their incompatibility. And for comparison, I'm showing you some kind of idealized patterns for terrestrial rocks that come from an enriched mantle or a depleted mantle or a mantle in a subduction zone that has been altered by hot fluids. And this is a mess here. It basically, I think we're seeing all of these patterns, but mostly enriched and depleted. But some of these, the only other data we have here are from gamma ray spectral measurements of thorium and potassium from orbit to compare with. The ages are probably a surprise. Most of these meteorites are very young. In fact, that was the argument that Stoper and I used. We couldn't think of a mechanism for melting asteroids so late in solar system history, so the young ages were the initial argument that these might be Martian meteorites. Many of them are less than 200 million years old. The Knocklites, Chassagnites are about 1.3 billion years old. By terrestrial standards, that's old, but by planetary standards, that's yesterday. And only the regolith Breccia, which has an age of about 4.4 billion years, and the Allen Hills 84001 have ages really stretching back here to the beginning of Mars history. The interesting thing to me here is that the crystallization ages correlate with the petrologic classifications. And what that may suggest is that each of these is a separate unit that has been sampled on Mars. The biased young ages are a surprise because most of the Martian surface appears to be very old, as judged from crater counting. And I think this reflects the difficulty in sampling by impact. You need a hard, coherent, maybe relatively young rock to be sampled. The ancient crust of Mars is old and highly fractured by impacts, and so you just cannot accelerate those rocks to Martian escape velocity, 5 kilometers a second, and allow them to survive that trauma. We also have cosmic ray exposure ages that are recorded once the rock is in space. They are all relatively short, and we interpret these as launch ages from Mars. And again, they correlate very nicely. There are a few exceptions, but most of them correlate with petrologic classification. So this suggests maybe 7 to 9 different launch sites, although we don't know where they are. But I will point out that 7 to 9 launch sites is a lot more than the 4 sites that we have visited with rovers. So there's still a significant sampling. So we might ask, how representative of Mars are these Martian meteorites? Mars has a basaltic surface, and these Martian basalts or Martian meteorites are basically basalts or related rocks, so that fits. But as I mentioned, they are much younger than most of the surface of Mars. So there's a difference. The other is there are a number of units on Mars. You just heard Liz talk about one of these that are interpreted as fluvial, lacustrine, evaporative, hydrothermal, aeolian, or pyroclastic. We have sampled none of these in Martian meteorites. The only sedimentary rock in the Martian collection, again, is this regolith breccia. Most of the clasts are basaltic. The lone sedimentary meteorite is mineralogically distinctive from Martian soils, and it really reveals little about the environmental conditions that were present when the great bulk of the clays and evaporite materials on Mars formed. It's an important meteorite telling us about the various early stages, but much of the interesting part of Martian geologic history is just not sampled by any of these meteorites. This is a familiar plot of alkalis versus silica that petrologists use to classify volcanic rocks. And what I want you to see here is all of the Martian meteorites are in these blue or purple colors, and they all plot down here in the field of basalt, or some of them in picrobasalt, except for all of these triangles here, which are the regolith breccia, and these are classed within the regolith breccia. And you can compare those with the samples, the igneous rocks that have been analyzed on Mars by rovers at two sites, at Gusev's site by the Spirit rover, Gale by Curiosity, and the green line here is the boundary between subalkaline and alkaline rocks. And what I hope you can see is that all of these rover rocks are either mildly or strongly alkaline, whereas the Martian meteorites are subalkaline. There's one exception. We have one sample on Mars that looks like the Martian meteorites, and we have one meteorite that looks like the samples that we have analyzed on Mars. And interestingly enough, if we look at the ages of these, the Martian meteorites, everything that I've enclosed here is young, that is less than about 2.4 billion years old, most of them less than 1.3 billion years old, whereas everything outlined here is old, greater than 3.5 billion years old. So what this suggests is that Martian magma compositions have evolved over time. The source regions are different as well. Just one example, here's a plot of nickel versus magnesium and manganese versus iron. These are geochemically similar, but the trend for rover analyzed rocks is different from the Martian meteorites, and ditto over here. Another, maybe it's a surprise, is that we have no samples that indicate calc-alkaline magmatism, which is so important on the Earth. Here is a plot, total iron over magnesium versus silica. Here's a boundary between calc-alkaline rocks and tholeiitic rocks. And calc-alkaline rocks, basically the magmas with increasing partial melting form compositions along the big arrow here, and then as they undergo fractional crystallization, they move up along these arrows here. We see nothing like that on Mars. The Martian meteorites and the rover analyzed rocks all plot in this area here. We have no detectable granitic rocks. Of course, we haven't found any granitic rocks in the Martian meteorites, but here's a a gamma ray spectrometer map of much of the surface of Mars, looking at the abundance of the element silicon. And here's the key. We're not used to thinking about silicon as geologists. We used to thinking about silica, but to give you a reference, granite has greater than 30 weight% silicon. And there's nothing like that, at least in the mappable part of Mars here, at the scale that an orbiting gamma ray spectrometer can tell. Here are the Martian meteorite silicon values, and they basically more or less overlap what we're seeing here. There is no Earth-like continental crust on Mars, despite some work that has been published that argues for that. There are clearly a few silica-rich rocks that have been found in Gale Crater between 60, these are diamonds here, between 60 and 70 weight% silica. However, they don't look anything like the ancient continental crust, which is represented by these Archean TTG rocks here. In fact, they look like highly fractionated rocks that form in from plume magmas, such as in Iceland here. You see all this trend here, and they fall right along that, as do the samples from the Northwest Africa 7034 regolith breccia. And then finally, despite much ado about purported evidence for Martian life in this Allen Hills 84001 meteorite, the evidence, which is the organic matter, which is very complex material that could have almost any origin, the unusual morphology of some minerals, particularly some very small magnetites, which are similar in some cases to some biologically produced magnetites, and some intriguing morphologies that have been proposed to be microfossils, or actually they're too small to be microfossils. They would have to be pieces of microfossils. All of the evidence for all of these things have been shown to be more consistent with abiotic origins. So unfortunately, the Martian meteorites, although they have helped to infuse a lot of interest in Mars exploration, and particularly a Mars exploration program focused on the search for life, they haven't really helped us that much in that search. So to conclude, Mars is a basalt-covered world with sediments derived from basaltic protoliths. The Martian meteorites are basalts and related cumulates that reflect diverse ancient mantle sources. The comparison of young meteorites with ancient rocks analyzed by rovers indicate that magma compositions have evolved over time. The magmas appear to be plume-derived, and without subduction, there has been no calc-alkaline magnetism, nor any Earth-like continental crust formed. And finally, Mars meteorites increase the identification of some Martian minerals, but biased impact sampling limits our knowledge. So my bottom line for that is the same as Liz's. It's time to bring back some samples. Thanks very much.